Greetings everyone, and welcome to the very last video in our little lecture series on Stat157. This video is going to be an example of how to do confidence intervals. Just the bare bones basics because we're wrapping this course up quickly. Okay, so our example is 40 students were asked how much time they studied over the weekend before final exams. The mean was found to be 15.1 hours. Using my highlighter pen, here's the mean, and the standard deviation was found to be 6.5 hours. We're going to construct confidence intervals for the mean time studied over the weekend, and I suppose I really should change that wording for all students with. So the idea here is that we've got sample info, and what we want to find is the population mean, or rather to estimate it based on incomplete information. So we have sample info, we want to estimate the population info based on the fact that we haven't measured everybody for some logistical reason. We've only measured some of them. Now, a couple of things that you might have noticed is that we don't actually have any information on what the distribution is for the sample info. We don't know if that distribution actually looks mound-shaped or not. But what we're using is a large sample, and our number of students up here we've found to be 40. If n is greater than or equal to 30, then we can just go ahead and calculate this even if we don't know what the distribution is for those 40 students. Is it flat? Is it skewed? Does it have 2 bumps, all the people who studied both days versus 1? Or does it have a bunch of outliers? We don't really know, and we don't need to know. That's the kind of nice thing. So we're going to construct confidence intervals for the mean time studied the weekend for all students. And I'm just going to scroll down here. With 90%, 95, and 99% confidence, and then we're going to finally answer the question, what happens to the size of the interval as the confidence level increases? Okay, so answer. For 90% confidence interval, I should label that as part A. Part A wants a 90% interval, and I had given you a table earlier of what the associated z-scores are for various intervals, and if you look up what the z is on that table, then you get the value 1.645. Alternatively, if you like, you can throw this into the online calculator. You can find out what the area is. If you put the area of 0.9 or 90% in the calculator and go from probability to values and choose the z being evenly distributed across the mean, then you'll get 1.645 out of that calculator. Honestly, it's easier to just look it up in the table. And then we go ahead and we write down the formula for the confidence interval, which is mu is equal to x bar plus or minus z sigma over the square root of n. Now here I also said that if you don't happen to know sigma, then, whoops, I wanted to use a highlighter pen there. If you don't happen to know sigma, then we're going to use S, and the reason that we're allowed to do that is because, again, we've got a large sample, and we're allowed to do that substitution for large samples. Smaller samples become a lot trickier, but that's beyond the scope of this course. And now we have done all the thinking that we need to do. We're just going to plug in some numbers. Our x bar, we said the mean was 15.1 hours, and we're doing plus or minus the z we just found to be 1.645. Our standard deviation was 6.5 hours, and then we're dividing by the square root of n, and if you'll recall, there were 40 students. So when I throw that into my calculator, I get 15.1 plus or minus 1.69063, which I hope that everyone agrees is a ridiculous number of sig figs, or decimal places if you prefer. And so we don't actually want to round that in our answer, because this seems to imply that we actually know it down to a ridiculous amount of precision. If you take a look at, the 5th decimal place and all the rest of it, our calculation doesn't really support that, because we only knew the mean and standard deviation to the 1st decimal place. And so a reasonable thing to do, now there are more complex rules for doing this in advanced courses, but the one that we're going to use just for efficiency here is we're going to say that I gave you the mean to the 1st decimal place, and so you should round your margin of error, which is the thing after the plus or minus, the number after the plus or minus, to the same precision. Or if you want, you could give me 1 extra decimal place and write that as 1.69. But it really doesn't make sense to write 1.69063. Now, this is not your answer yet, because in order to give it as a confidence interval, we actually have to write it in the following way. We're going to take 15.1 and subtract the 1.7 to get 13.4. That's the lower limit of our interval. And then we're going to take the 15.1 and add 1.7 to get 16.8. That's the upper end of our interval. And then we're going to write the units, which is hours. So notice this is an interval from the lower limit to the upper limit, and that gives us our confidence interval. Okay, so that's the answer to part A, that we believe that with 90% confidence that the answer is somewhere in there. So for part B, it's the same calculation, but with 95%, that implies that our z-score is not 1.645 anymore, it's 1.96. And so we write that mu is equal to x bar plus or minus z sigma over the square root of n. We replace sigma by s. We throw in our values again, and the only thing that changes is we get 15.1 plus or minus 2.01437. And we're going to do some nice rounding here and say that that's 15.1 plus or minus 2.0. And so remember, that's not our final answer. The confidence interval is equal to 15.1 minus 2, so 13.1, to 15.1 plus 2, which is 17.1 hours. So that's our confidence interval for 95%. And then part C, we want a 99% confidence interval. That implies that our Z now is equal to 2.575, again looking it up on our chart that we did earlier. So we get mu is equal to, let me use blue. Mu is equal to x bar plus or minus z sigma over the square root of n. And again, same calculation, but replacing with our new value of z, and you get 15.1 plus or minus 2.64643. And then appropriate rounding again says 15.1 plus or minus 2.6. Now we have to, of course, write out our confidence interval. So our confidence interval then is equal to 15.1 minus 2.6, so 12.5. And then 15.1 plus 2.6, which gives 17.7, and then our units are hours. And now we're going to do the very last part. The last part asks what happened to the confidence interval, the width of the interval as the confidence level increases. You can see that it gets bigger every single time because just scrolling up, we initially had 15.1 plus or minus 1.7, and then it went to 15.1 plus or minus 2, and then it went to 15.1 plus or minus 2.6. And so as the confidence level increases, the width of the interval also increases. And so that's answered our question, but a good reason, a good thing to ask is, why would that be? So you can imagine that, suppose you have a bunch of data points, and you've decided that the mean of those data points is 15.1, and you're trying to determine where the mean is, and you're making a guess. Well, you could say, I'm pretty sure that it's within this interval. That's our 90% confidence, which means that, 10% of the time I'll be wrong and I'll be outside of that. But if I want to be really, really sure that I've captured it, I can make my interval really wide. Or, well, just make it a little bit wider, but I'm grossly exaggerating the difference here. But if I said, 99% confident, I'm really sure it's in here somewhere, and it's only going to be 1% outside. But notice that the utility of this interval goes down as the width of the interval goes up. So let me give you a different example, which is, suppose we were trying to, I don't know, estimate the temperature in Victoria tomorrow or something like that based on past measurements or something like that. Then if I say, I believe that the average temperature in Victoria was greater than 0 Kelvin, clearly I'm going to be right all the time because we can't have temperatures at 0 Kelvin or below. If I say it's going to be between negative 40 degrees Celsius and 40 degrees Celsius tomorrow, since it's April and it just doesn't get that hot, chances are still pretty good that I'm going to be right. But if I say, oh, it's probably going to be, I don't know, around, 15 degrees Celsius, then the fact I'm giving you more useful information, you can determine whether or not you're going to need a jacket. But the chances, when I've narrowed it down, the chances are much higher that I might be wrong, that, I'm making a prediction based on incomplete information, and the smaller the interval that I say, the more likely it is that there could be an outlier and I'll be outside that. So if I want to absolutely be right, I make my interval huge, and I say I've got 99 or 99.9% confidence. But if you want a little small interval, then the chances of you being outside that interval are much higher. Similarly, if we take a look at our equation, and we say that mu is equal to x bar plus or minus z sigma over the square root of n. Let me write that better. Note what happens as my sample size changes. If my sample size starts getting really large, then my margin of error, which is the entire term after the plus or minus, gets smaller. And that makes sense because the more data that I take, the chances of me just having a single outlier, which is skewing my mean, or having a number of data points that are all below and not any above to balance it or something like that, that when I have a small sample, my chances of being wrong are much higher. But if I take a very large sample, as the size of my sample increases, then the precision of my estimate will get better. Anyway, so that wraps up what we're going to be doing on confidence intervals this term.